Hello, my name is Craig Bigman, and this is a companion lecture to the Lime Water lecture that I intend to present at MACNA 2022. The content of this lecture was actually excerpted from a talk that I gave in New Orleans in 2017. And that talk was reef keeping by the numbers, and I talked a lot about calcification model and nutrient dynamics in reef tanks. I pulled the nutrient parts out of the talk, kind of streamlined it a little bit. So let's get into it. Why am I interested in these subjects? Because in aquariums, nature speaks very, very loudly. In these little glass boxes, we can understand a lot about how the world works, and how coral reefs work, how they stay alive, what they need, observe the organisms every day. And in particular, the chemistry is extremely amplified in small systems. So that makes them really interesting to me as a biochemist. This is the equation for calcification, and it's the equation that I've spent a fair amount of my hobby career chasing down the details of. So 1 calcium ion and 2 bicarbonate ions create calcium carbonate, carbon dioxide, and water. So that's what happens when corals calcify from natural seawater, which has almost exclusively bicarbonate ions. So 2 to 1. That's important. There's 2 equivalents of alkalinity depleted from a reef tank for every 1 mole of calcium that's removed. So, among other things, I started representing the calcification situation in aquariums in a graph like this, where the vertical axis is often chosen to be calcium, and the horizontal axis is alkalinity. So, in this case, the slope of the line is set by the alkalinity loss. So a balanced loss of calcium alkalinity or a balanced gain of calcium alkalinity slides the system along one of these diagonal lines. And unless something happens if you're using balanced calcium and alkalinity supplements, unless you do something to change that balance, your system's kind of trapped on one of these lines. It's going to slide up and back and up and back. So if you add lime water, you'll boost both calcium and alkalinity. Corals calcify, both will be lost. So this is confusing to people. They don't necessarily get where they expect to be when they add calcium and alkalinity to a tank. So it may be useful to think of some arbitrary box that we want to drive our system into. And you can make this box as generous or small as you want. The parameter space for keeping corals alive in aquariums and happily growing is relatively wide. What seems to be most important is stability around whatever set point you choose. For the purposes of our discussion, we could choose a set point on the green dot, which represents natural seawater conditions. So a little bit under about 2.2 milliequivalents per liter alkalinity, a little bit over 10 millimolar calcium, which translates to about 420 mgs per liter calcium on a trivial concentration unit. If you want to convert to DKH, you can do that. The numbers are really good, are ugly and obscured to me. I prefer the mole-based or the concentration units that are arrived at by basically counting the number of ions in solution. And that makes it really easy to map the implications of chemical equations onto the performance of the system. So that's how I devised this graph. If you want to, you can see what happens if you're outside the box and you add calcium, you move along a horizontal line. If you add alkalinity, I'm saying you move along a vertical line. If you add alkalinity to the system, you slide the system horizontally, and you can maneuver yourself into the box by adding one or the other, and then allowing calcification to occur and sliding you back into the green zone. So this is a useful graph to look at if you're trying to understand what happens with your system and what to do if the numbers are out of whack and you have a different target. The next thing to realize is that calcification in the reef tank and on coral reefs is really fast. Typical reef aquarium will come in somewhere between 2 and 20 kilograms per square meter per year. And I've informally called this a calcification unit to make it a little bit easier for people to get their heads around. There's a lot of exponents and units of measure that people are probably not entirely comfortable with. But like people can use par meters just fine, right? So they read out in micromoles of photons per square meter per second. And you guys don't know what so then people call that like a par unit, right? So the molar part of it is kind of obscured. You don't have to worry about it. And that's a very popular way everybody knows about par, right? So everybody should know about calcification units as well. So 2 to 20 is the number that we usually have in reef tanks. So this has huge implications for water chemistry. And towards the upper end of that range, the carbonate alkalinity in a system can easily be largely depleted over the course of a single day by the growth of stunning corals. So this is a wild ride that you guys have signed up for, where you have these top flow, top light, SPS heavy aquariums. And the purpose of this talk is to let people know what they're getting in for, right? What are you signing up for when you design an aquarium that way? Is that really what you want to do? Do you want to work that hard, or do you want to invest that much in the technical equipment that's going to make that possible? Maybe not. At least you should know what you're getting into. Okay. So there's a simple model that Marlon Atkinson and I started using in the 90s to describe what happens in aquariums. And Marlon was studying the biosphere 2, and I was studying, kind of like diverse reef aquariums in the hobby. And it appeared to everyone that this model actually performed pretty well in predicting outcomes in aquariums. And it's remarkable that such a simple model will actually work, because there's a large kind of scatter in flow and illumination and a bunch of other factors between different reef aquariums, between different aquarists. But you still get within probably a factor of 2 of the correct number, or the observed number, when you apply this model. So the model is that corals calcify at about 10 kilograms per square meter per year, so 10 calcification units. Coralline algae calcifies at about 4 calcification units. Sand area is neutral in this model. It has 0 calcification units. Calcification happens only when the lights are on. It stops when the lights go off. And in the simulations that I'm doing, the calculations that I'll present assume 100% coral cover. Okay. So we'll do some time courses on aquariums and kind of understand what this looks like in simulated reality. Okay, so one of the interesting things that fell out of this, because we're looking at projected area, right? So the magnitude of the excursions that people will experience during the course of the day for an all-in-one kind of system where there's no big sump somewhere else, right? It's just the display tank water that we're talking about. The way things fall out is that the magnitude of the daily fluctuation is just inversely related to the depth of the aquarium. So shallower aquariums experience larger fluctuations. So this is the red line is aquarium that's one foot deep. Okay. The yellow line is an aquarium that's 2 feet deep, and the green line is an aquarium that's 5 feet deep. So it makes a big difference, right? So the frag rack things, the frag grow out trays that people have where the corals are in really shallow water. I hope you got a sump, or I hope you've got really good active control over calcium and alkalinity in the system. Otherwise, that's going to be a hard system to hold on to, right? Because that's the worst case scenario. Rapidly growing corals in shallow water. Other choices affect system stability. So one choice that you might make is to run your system at slightly elevated alkalinity to provide more stability, more buffer. Yet another choice that you might make is to continuously dose calcium and alkalinity uniformly during the day. Okay. Or you might decide to discontinuously dose calcium and alkalinity, like with balanced 2-part supplements, and you're just going to like dump them in once a day. Okay. So the calcification rate for these two aquariums is identical. But as you can see, the green line above, where the system's running at elevated alkalinity, 4 milliequivalents per liter, and calcification support is being dosed continuously through the day, experiences much smaller excursions than the dump once a day kind of system. And at the end of the day, the alkalinity is getting like really too low in the system. Below 1 milliequivalent per liter is really not good for corals. And this is a large daily excursion. So husbandry choices can make a big impact on stability. Okay. So the results, the kind of like take home from the simulations, the numeric simulations that I did, is that systems that are chock full of corals will rip through almost all their alkalinity in a single day, unless you're doing something to supplement it, or you're running at really elevated alkalinity. Okay. For this simple model, water depth in an all-in-one system is a really critical parameter, because that's just water depth is linearly related to water volume, right? So more water volume damps out these fluctuations, because in the model, the corals are distributed on a surface. So what the surface area at the bottom of the tank projected down, right? Versus the whole volume of water. So deep tanks may have a stability advantage. Shallow coral grow out systems, these frag tanks are the worst case scenario. Your choices about community structure, what you put in your tank, how much open space there is, have a large impact on the daily alkalinity fluctuations in your system. And obviously having a big sump, because you're adding calcification, inert water volume, where there's no calcification happening, definitely decreases alkalinity fluctuations. Okay. Pulsing, pulsatory addition, once a day addition of two-part solutions leads to larger fluctuations than dosing them continuously during the day. Small systems may need to run at higher alkalinity for stability purposes with pulse additions. Okay. So I've asked people if they're interested in completing a calcification survey, and you'll find that on the webpage, my webpage for MACNA 2022. Okay. I've asked these questions a few times over the years, and I've continued to accumulate data. I'll show you some of the data from some systems so you get kind of a handle for what I'm looking for, the objectives of the calcification survey, and decide if you want to participate and know more about your system through participation. Okay, so these are the systems. Terence Fugazi was very generous with his time and worked really hard on giving me some great numbers for his tank. And we're not only looking at calcification, we're also looking at nutrients in these cases. So these individuals worked extremely hard to give me these numbers. Appreciate it very much. Okay, so in Terence's tank, his reported species breakout is as follows. So it's like 12% hard coral, 0% soft coral, 25%. Kind of, as you look down the tank, 25, you'd see 25% of the rocks covered with coralline algae, and the substrate is roughly 2/3 of the area that you would see looking down. So the prediction in this case is that this system would calcify at about 4 calcification units. The observation was that Terence's system is actually calcifying at much higher than that, about 9 calcification units. And I think the discrepancy for this is that Terence's aquarium is very three-dimensionally open, and the corals get good flow and are calcifying really at maximum rate. Okay, so this is a system that overperforms relative to the 1040 model. This is some data from Sanjay. 85% hard coral as you look down on the tank from the top, about 10% coralline algae, insignificant amounts of clams and rocks. So the predicted calcification rate for this system was about 9 calcification units, and Sanjay observed about 11 calcification units. So that's pretty close, right? The model did pretty well in this case. And in his case, looking at it a little bit more, I think that the coral rate in the system is about 13 calcification units. So this was Randy Donowitz's main reef at Pratt University. This is a really famous system, and a number of these systems that I'm describing are fairly well known. When Randy did the survey, the hard coral covered about 75% of the projected area of the aquarium. The predicted calcification rate was about 7.5 calcification units, and the observed calcification rate was about 7.4. Okay, so it was like right on the money for this aquarium. This is MetroCat's aquarium back in the time machine in 2017 now. So her breakout is as follows. She had about 40% hard coral, 15% soft coral, some coralline rock, no clams. A quarter of the tank, as she reported it, is covered with substrate. It actually looks like it may be a little bit more than a quarter to me looking at this picture, but whatever. She's using 2-part supplements, and the modeled rate for the system was about 3 calcification units, and she observes 2. So the model performs well. Another tank from Chris Roberts, similar sort of calcification prediction is 5 calcification units. The observation is 5 calcification units. Okay, so and then Jason Langer's aquarium in 2017, the observation was the prediction was maybe 5 calcification units. The observation was around 2. So the model was a little low in this case. I'm not sure exactly why that is. But like I said, light and flow, exact species of corals that are present, all of these are going to affect the rates. And these composite numbers are to get you in the kind of in the right ballpark. Okay. I think they're useful in system design. They're useful, for example, in predicting how much lime water your aquarium is likely to need and whether or not lime water is likely to work out for you, or if you're going to have to need something else. In conclusion, this simple model, which was created by Marlon Atkinson and myself in the 1990s, continues to be relevant for understanding what happens in reef tanks and predictive. Okay. That I also was measuring food because I was interested in how much food was going in, carbon and nitrogen and phosphorus balance in the tanks. And the amount of carbon that was going in was less than calcification from food, carbon from food. And that's the story, guys. We can make these predictions. Predictions are pretty solid. This model's been around for a long time. It can help people now, even though it originally was created in the 90s. It's still relevant. If you want to participate, fill out the survey. At least now, even if you don't do that, you know what I'm talking about. You know what a calcification unit is, and the lime water graph. Hopefully that makes more sense to you now. So look forward to seeing everyone at MACNA, and I need to go to bed. Talk to you later. Bye-bye.